we can think about, a lot of us like to think about the Earth as the water planet, but that's kind of a misnomer because it's just this tiny, tiny thin layer of water on the surface of this big rock, right? So if you balled up all the water on Earth, you would get a ball about that big, right? It doesn't look like the water planet anymore, right? But when it's spread out into the oceans in this thin layer of water, it really does look blue. But I think this helps us understand just how finite water is on Earth. So the big ball is all the water on Earth. The medium-sized ball right here is all the groundwater. So if you look at all of the water on Earth, about 97% is salt water. Almost, a good chunk of that remaining 3% is groundwater. So that's what you see here. And this small, tiny little ball you probably can barely see, that is all the fresh water that's found in lakes and rivers. And so this is, again, kind of one of the reasons that I think studying fresh water on Earth is so important, because it's so rare. So there are more than 3.5 million miles of rivers and streams, and this includes what are called intermittent streams that go dry sometime in the United States, and approximately 40 million acres of lakes, ponds, and reservoirs. And if you push that all together, it would be an area about the size of New York State. More than 277 million acres, though, of wetlands, such as marshes, swamps, bogs, and fens. You can see wetlands make up a much larger area than either rivers or lakes, even rivers and lakes combined. And about 2/3 of all the precipitation that falls is evaporated or transpired back into the atmosphere. So the atmosphere holds, a lot of water vapor at all moments in time. But 1/3 of that precipitation that falls ends up in streams and rivers. But it's still a very small amount. And so here's another way to think about the water on Earth. If you have all the water on Earth, 97% is in the oceans, that leaves 3% for everything else. If you take that 3% and you break it out, about 77% of that 3% is in ice caps, glaciers, and inland seas. 22% of that is in the groundwater, and then there's only 1% of the 3% that's left over. So if you take that 1% of 3% and you expand that, you end up with 61% in lakes, 39% in the atmosphere and in soil moisture, and then just a tiny little bit is left in rivers. So here's another way to think about it. I like to show you lots of ways to think about it. We all learn in different ways. So we have 97% of salt water. The remaining 2.7% is fresh, but 2.14% is trapped in the ice. Only 0.001% is found in the atmosphere. 0.61% is found in the groundwater. 0.005% is found in soil water. 0.008% in saline lakes like the Great Salt Lake, things like that. And 0.009% is in freshwater lakes, and 0.0001% is found in rivers. Again, I guess I like studying things that are scarce. So here's a really brief schematic of the water cycle. It's pretty simple. We have land, and water evaporates from the land into the atmosphere. Water also evaporates from the ocean into the atmosphere. Once the water is in the atmosphere, it can rain down as precipitation on land or over the ocean. And once it rains down on land, it usually finds its way to the ocean eventually by moving through lakes and rivers in the groundwater. Okay, so all of these are flux values. We're going to use this term a lot. In this case, we're using cubic kilometers per year, okay, of water. And so this would be 423 cubic kilometers per year is evaporated from the ocean into the atmosphere. Here's a little bit more complicated hydrologic cycle. It shows you just a little bit more detail. Again, you have evaporation from the ocean, you have transpiration and evaporation from land. You have water storage in the atmosphere, and then it condenses and falls as precipitation. Water then is stored as ice and snow in the mountains. Some of that snow melts and runs off into streams. Other precipitation is involved in surface runoff. Some of that water infiltrates the groundwater and then is discharged from the groundwater into rivers. Some of the water in rivers is infiltrated back into the ground, and then you have other groundwater flowing out into the ocean. So it's a really cool cycle. It is driven by the power of the sun. The sun's energy drives evaporation. And what I like to think about is every molecule of water that's on Earth today has been on Earth since the beginning. We're not creating new water, and so we're just recycling it. So the water that we're drinking today was lapped up by dinosaurs and has been cycling since. So it's a humbling thing to think about the age of water and the recycling capacity of our planet. So unfortunately, humans have caused lots of problems. I'm going to try to keep, the focus on the problems and also on solutions today, but today very few rivers and streams are pristine. In fact, only 2% of streams in the United States are not affected by dams. 18% of stream miles in the United States are actually under reservoirs. They're not streams at this moment in time. They are submerged streams. And things like the decimation of beaver have significantly altered channel dynamics. And so we're really excited to see beaver reintroductions occurring. And then we also have a loss of large predators on land, things like wolves and cougar and lynx, that are influencing channel dynamics because there are more prey, like deer and elk, available to eat riparian vegetation and trample stream sides. So the loss of large predators has had a high impact on riparian zones. Here is a figure from the updated version of your textbook. So I'm often going to use figures and information from the updated version, even though the ebook that you're reading is an older version. It's free, so free is great. But this figure is from the newer version of the book, and I like it because it talks about the value of freshwater ecosystems. And so here we have value, US dollars from 2007, so updated but still a little bit old, right, per hectare. And so what you can see is that freshwater wetlands have really high value to humans compared to lakes and rivers. And there's global value too, and the global value actually of lakes and rivers is even higher. And so let's see, the relative values per unit area, this is by per unit area, and the global values by service for both wetlands and then lakes and rivers. And so there's more area of wetlands, and so they have higher value, but overall, I think some of the values, especially things like water regulation and water supply, are huge values for rivers if you look at it globally. So rivers and streams do lots of things for us. Climate regulation, water regulation, erosion control, nutrient cycling, waste treatment, habitat, food production, genetic resources, recreation, and cultural values. So there's a lot of reasons to do the work to protect these ecosystems. And it's kind of weird to put value on natural resources, but I think we're at a moment in time when we need to, because that's the money talks, right? That's the language that gets things protected. And so the global value of wetlands is over $1.5 trillion per year. The global values of rivers and lakes, $2.4 trillion per year. And these were estimated in 2014 by Costanza et al. The global value of irrigation water, $26 billion per year, and crops, $3.1 trillion per year. And the global value of fisheries, a whopping $112 billion per year, right? So there's a lot of value, economic value, in protecting these things. So we need to protect them because they have a right to exist on their own, but we also need to protect them because we get a lot of value from them. Unfortunately though, there are lots of threats to rivers today. So we'll talk about each of these things in detail throughout the quarter, but just to kind of give you a sense of the broad range of threats. Eutrophication is kind of nutrient pollution. Streamside development, huge problems. Water pollution, overharvest, logging and road building. Hydropower, which is both a benefit and a cost to rivers, right? Transportation, habitat alteration, invasive species, contaminants, over exploitation, and climate change. So all of these things, a lot of them interact with one another, make these really tricky problems to solve, especially for rivers, because of the human desire to be close to them, to live along them, to farm along rivers. All of this is really valuable. So we're also living in an era of increasing water conflict. So this is showing through time the number of human conflicts over water per year has just started to increase, not quite exponentially, but we're getting there, right? So especially since 2000 and climate change impacts becoming really present for a lot of people over the globe, we see the increase in water conflict. So this is kind of dipping into political ecology, dipping into understanding warfare. I think this is something that we're going to see a lot more of as we study water. So the biggest challenge, in my opinion, is reconciling the needs of humans with the needs of aquatic ecosystems. These things are in conflict a lot, and so we need to figure out how to live with rivers, giving them space to do what they do naturally. So we need good science, we need good management, we need protection and conservation, we need restoration, and these are tasks that are at hand. And now you just need the tools to go out and do this good work. So this is your first step, being in this class. We're going to learn a lot about freshwater ecosystems, and then you'll have skills that will help you when you get out there and do the work. So the knowledge of the ecology of systems is essential to making good decisions. And I think this is really crucial.